Hello, welcome to lecture number 15 on explainability. So this is the last lecture in this class, and we're going to cover some problems about, once we've built all the models, what do they actually mean? And what that gets us to is explainability. So I'll first cover a little bit, what it actually means to explain a model. Then we'll look at a couple of simple strategies in terms of, finding simple functions. Then we'll look at statistical dependencies, for instance, conditioning and backdoors. And in the end, we'll look at some more modern approaches such as SHAP, integrated gradients, and some heuristics. So people have looked for explanations for a very long time. Probably one of the best known ideas from 2000 years ago is Platos Cave. So in Platos Cave, this is of course written in Latin because that's how people used to write this at the time for when this was Antrum Platonicum. The idea is that you have some fire, and that fire illuminates reality. However, the people here in the audience only get to see the shadows of what really happens on a wall. And so their goal is now to figure out what might be happening in reality based on those incomplete projections of reality. So this is probably one of the first examples of explainability, namely trying to take some non-necessarily apparent data and use it to infer how reality really looks like. And quite honestly, this is a problem that hasn't really changed very much since. Okay, so once we have all those very high-minded ideas, well, let's look at something that's a little bit more practical. So this is something that happened to me when I arrived in the United States. So we freshly arrived, and I got a job as a scientist at Yahoo Research. And of course, just like everybody else in the United States, I needed a credit card. And unfortunately, I was denied the credit card. Well, why? Well, so I actually was very frustrated. So I went to the bank and said like, well, look, here's my bank account statement. I can easily pay this. By the way, here's my paycheck. I can easily pay for the monthly payments. So would you please give me a credit card? And they were like, no, you have bad credit. I'm like, no, I have no credit. And they're like, well, yeah, that's exactly what bad credit is. And so basically I was in this catch-22, and well, let's just put it this way, banks take quite some advantage of that. And in order to get to a good credit rating, which, is achievable, you then, go online, you look at, how actually this credit score is being composed, and then it tells you, okay, well, how much credit you have available, how long you've had your accounts, and all of those things. And so it's heavily stacked against people who newly arrive in the place, but basically after a while and after you play the game, you're okay. So what I did is I basically had the observation of credit denied, and I then went on and basically, like everybody else, I gamed the system. And as a matter of fact, well, this is being taught as, financial literacy, namely, hey, use gasoline credit cards or place utilities in your name and so on in order to get to a good score. Once you're there, well, how to maintain a good score? Well, basically pay your bills. But then also do weird things like only spend 1/3 of your credit card limit and, apply only for credit when you need it. So it's basically a lot of really strange recommendations. And it's a strange explanation for the model that generates a credit score. And I think we can all agree that this is only to a limited extent a model that causally explains why you should or should not get credit. Which, by the way, ties in nicely with the previous lecture where we looked at credit scores and, whether you actually get a loan. The banks aren't that stupid either, so they also use other parameters to decide whether you should get the loan rather than just by stratifying by the credit score. Okay, so what happens more generally is we have some estimation problem, we have some data, we train some model F. And then afterwards, we may be interested in the following types of questions. One is, well, what does this function f even mean? So let's say I'm Georg Simon Ohm, so the guy of Ohm's law, and I have, a couple of things that I can let electric current through, and I measure the current and the voltage. Then what I am after is actually a natural law, which, well, is now named after Ohm's law, namely the proportionality between current and voltage, and the proportionality constant being, well, the resistance of the object. So that's the very general, in principle, explanation of what's going on. And in this case, explanation of a natural phenomenon, which then follows Ohm's law. The second thing that you may be after is you may want to know which features actually affect the output. So this is basically a situation where, let's say, I train a model and I train it on, maybe the color of your hair, but also your bank account and other things. And obviously the color of your hair shouldn't really affect creditworthiness, versus the color of your hair may very well affect whether you get a sunburn or not, but your bank account shouldn't. So this is an example of how you may want to ask, given some model, which features and in which way actually affect the outcome. Now, what happens though is that, especially when the functions are nonlinear, you can't just say, well, some feature is really meaningful, but it may only be meaningful within a given context, and it may not necessarily be linear. So for instance, let's take body temperature, right? So if you were to, let's say this is 37 degrees Celsius, and what you would probably get is a situation where the amount of sickness will go like so. In other words, it's a really bad idea to have a really high body temperature, because then you have fever, and at some point, your proteins in your body start to denaturalize and you die. But it's also clear that if your body temperature is too low, you die. So for instance, people will die from hypothermia. They will die if they, fall into cold water, and then they just lose body temperature and their body shuts down as well. And so what you would have, and so this is basically sickness, that you might have maybe something that looks locally like a linear function here, right? And of course, if you were to extrapolate that, the recommendation would be to freeze everybody, because then they're the healthiest. Likewise, if you were to extrapolate for somebody with hypothermia, like so, then the recommendation would be to boil everybody, because then they're the healthiest. And it's patently obvious that both things are nonsense. But locally, you can argue that, let's say, if you have 38.5 degrees fever, then maybe reducing, the temperature by half a degree or a degree, makes you correspondingly healthier. Right? In any case, so this is why you may want to explain things locally, or you might want to explain, why are Alex's credit ratings poor, as opposed to, what makes good or bad credit ratings. And I don't know exactly all the parameters that go into the credit score, but you could argue this way too. So here are some ways how you can look for simple models. Well, in the easiest case, we can have, for instance, a linear function, right? So it's like Ohm's law, but except that we have, it's linear in every one of its parameters, and there's some offset. So I just have W transposed X plus B. And of course, I can look at those coefficients Wi, and if they are positive and large, I could infer that maybe the xi's have a positive influence, whereas, if they're very negative, then, well, I could imply that they have a negative influence, and if they're zero, then I could say, well, there's nothing there. And so, in other words, the weights tell us how important some feature is, and the covariates xi's tell us how strong this is for a specific x. Now, that sounds really great, but we still have problems. So for instance, if you have images, okay, it's pixels. I mean, obviously nobody would be as stupid as running a linear model on images, but on microarray data, you might very well do that. and people have done that for quite a while. Or, for instance, in time series, in a linear model, linear autoregressive model of higher order, so people still use ARIMA models and similar things, you might use that to infer how locally features affect, global mix prediction. Okay. Now, if you do that, you could even try to come up with even simpler models. So, for instance, you could just impose an L1 penalty. So this one norm here, right, does nothing else than just compute sum over I going from 1 to n wi. And we can clearly see, if you were to look at the corresponding loss function, that only for the value 0 here, we really get, a minimum of that penalty. And so this will encourage us to nuke WIs that are small and don't really have a lot of impact. And there's a lot of really good theory for it. And you can basically prove that if your problem is really sparse, then you're going to recover it. And then there are lots of persistency results. It's really great work. Now, if you have something that's a little bit more interesting, more structured, even for that, it still works. So, for instance, you could have a situation where you might want to say, well, I have a matrix of entries, and I want to have matrices where either entire rows are eliminated or entire columns are eliminated. So actually, this is a little bit of a typo here. You probably want to have a 2 norm there. But basically, you can design meaningful structured norms, or for instance, where you might say, well, if possible, remove an entire group. And if, that doesn't work, then okay, well, you better still remove individual terms. But this is, a hierarchical group penalty. There's hierarchical and structured lassos, and there's a lot of really good work that's out there, which, discusses whether you can solve the problems or not. And basically, the 90s and, early 2000s were full of amazing results on this topic. The fact that maybe you haven't heard that much about it is that, well, by now people use a lot more frequently nonlinear, non-parametric functions. And yeah, that's what you get. But you can still strive for simplicity this way. Now, in some cases, however, even especially if the problem is very high dimensional, this is still too complex, and linearity is not always a really good model anyway. And that makes it not always suitable for humans. For instance, it could be really tedious to evaluate a sum over 100 terms. It may be difficult to understand because even though we have linearity, we have multiple terms, they may interact. And this makes it difficult to operationalize in a stressful situation. So what people have done is they've built models that you can use even under a lot of stress and that are much, much simpler. So let me give you an example. So when you want to learn how to go diving, then you basically want to make sure you don't suffer from decompression sickness. So that means, if you spend too much time underwater and then you come up too quickly, or you go diving too frequently, then, you can really get very badly sick. This gets even worse once you try to do nitrox diving or trimix diving. So basically, if you mix a variety of gases, and essentially you have to solve partial differential equations of the gas level in your blood. Now, most divers that I know of are not particularly good at partial differential equations, right? They're good at swimming and other things, but PDEs, not so many. I don't think I've met even one. Now, the thing though is, if you, obviously nowadays, you just wear a dive computer and you look it up and it tells you exactly, how long you need to wait until you can, for instance, get on a plane or drive. But before that, people use tables. And so they would do stuff like to look at, at which depth, they were, let's say 70 feet depth, and they, would spend a certain amount of time there, and that, would get them from dive category E, apologize, it will get them to, the corresponding other terms. And I'm, skipping the details there, but essentially what you can do is you can then, work out, for instance, from here, how long you need to be on the surface and basically, or, decompress and do various other things. So these are really useful numbers in order to keep you safe. Now, this is a very simple table, very simple lookup table that allows you to decide whether you can dive or not, or how long you're still allowed to actually stay underwater. And this way, people even without PDE knowledge and without the calculator can easily read up things, and these letters are then what's being used as a proxy to find out in which what's called dive category you're actually in. Okay, now you might say, well, okay, not everybody's a diver. Well, here's another example. Let's say you're in an emergency room in a trauma center and patients come in and some of them have burns and some of those burns are horrible. You need to be able to triage reasonably quickly whether you are able to save that person's life or whether maybe you just give them a lot of morphine to reduce the suffering. And what's being used quite often in this case is something called the rule of nines, and you estimate very quickly the entire body surface and you look at how much of that body surface has been burned, and if it's too much, then if the patient is too old, then chances are quite dim. Now, if you look at the numbers specifically, you'll see that they're all multiples of fractions of 9, so that's why it's called the rule of nines. It's also because, the corresponding number of areas. And so every major body part, like every leg, has 18% of the skin. Your front and your back have 18%, your arms have 9%, and then, well, your head has another 9%. Now, this is, and then to just make the math work, well, there's the remaining 1%. So you use that to quickly guesstimate what the burned area is. So obviously it's not accurate because maybe my arms are very skinny, somebody else's arms are really bulky because maybe they work out a lot or maybe they eat more, who knows. But this gives you a good guidance in terms of their survivability. It's easy to remember even in a stressful situation like an ER, and therefore people use it. And it also gives them simple explanations. Are those models necessarily the most accurate? Well, of course not, but they can be used quite easily, so they're popular. Here's another example, and Cynthia Rudin and co-authors have done a lot of work in this context, namely to use essentially combinatorial optimization to find very simple functions. For instance, decision trees, so like, am I hungry? Yes or no? Well, no, then sleep. Yes, well, if I have enough money, well, go to a restaurant. If I don't have enough money, well, buy a hamburger. Or a simple decision list, which just goes like, if this, else, if this, else if, right? So you can basically write this as else. So everybody's programmed this, something like this at some point. Now you can see how you can use, this binary code for it. This is clearly not the most efficient code to encode, 4 possible outcomes, but it works actually quite nicely. In any case, so these are super simple models, and in those cases, people often very willingly trade off fidelity of the model for simplicity and explainability, because the context in which those models are being deployed are often such that that's the only way to go about it. Now, if we don't have such simple models, well, in some cases, we can actually approximate it. And so here's a simple alternative to finding those very super simple models outright. So for instance, it could be that you have a lot of prior knowledge about invariances and you can build a really good AutoML system that gives you a very high accuracy. As a matter of fact, we did that last year. You basically go and build this very, very high quality teacher model. And then you go and try to distill from that teacher model a student model that is very simple, and that's very close to the teacher model. So remember, Mu covered the distillation problem in his class. So I'm not going to go a lot into detail, but you basically have some loss function here that measures this difference between the teacher and the student, and then you minimize over the student. Such that the discrepancy between teacher and student is minimized. Right? You can sometimes do self-distillation and all of that, but we're not going to get into this. This is really just that. The question, though, arises is, well, if you do that, well, why don't you just train the simple model outright? We actually compared, and it turned out that if you train the model outright, you don't quite get the same accuracy. So let me explain what's going on. What you can do is you can train a random forest. So those green models here, they are all trained outright. And these red models are obtained by distilling from the true teacher. So this is the teacher, this one here. And for a decision tree, you get a significant lift, right, by about, 0.015, which in this case is quite high, between a tree that you train directly on the data or a tree that you distill from the teacher. And a similar thing happens to be the case, for instance, for, neural networks or, cat boost or, light GBM. So the only case where this was a little bit different is this one here, and that's just because the reference model was different. Okay, so what this really should tell you is that if you go and train and then distill, you get very high accuracy and you get a fairly simple model. So that's also quite nicely illustrated by the latency plot, where you get something that's faster and still highly accurate from that. Okay, actually, correction, this green circle here is the model that you get by combining all the various models. So this is basically a AutoML model combination, and that does really well. This is if you use the GIB sampler to augment the data. So let me actually explain what that augmentation is all about. So when you look at the training data, let's say you get a few data points like so, and you want to train a model, then it's very difficult to figure out, for instance, what might be going on here. But what you can do is you can sample around the original data to augment the data set. And now that more augmented data set actually works significantly better as a reference to distill from teacher to student. The question is only, how do you get that augmented data set? And one way to do it is to simply perform GIB sampling, where we take the original data, let's say we have x, and we now replace the ith coordinate, where xi new is drawn from p of xi given x without I. And you can get that, for instance, from, some transformer density estimation or whatever. Now, this means that you're starting to perturb one coordinate at a time in order to get, a better model, or at least get data that's very similar to the original data, but not quite the same. And that allows you to explore the neighborhood of the original data. If you do that, you get a model that actually works quite nicely. So GIB1 means that we've taken one step of GIB sampling, but obviously you could take, more elaborate steps, and that allows you to explore the trade-off between modifying one feature or modifying multiple features. And of course, if the fidelity of your density estimator is really good, then multiple steps work. If the fidelity isn't that good, then probably you can reduce the bias, but then pay for it with a higher variance, namely by sampling around it. Okay, so this is essentially what happens on the data. So that wraps it up for attempts to solve the explainability problem by taking a complicated model and transforming it into a much simpler model that, for instance, can explain or at least approximately explain what's going on, and that much simpler explainable model can then be used for ulterior motives, such as giving it to a human that can operate on such data in even stressful situations.